Ladies and gentlemen, I'm so sorry. First of all, I have to confront you with two problems. Problem one is easy to solve if you solve problem two. Problem one is to understand my Hoverwing technology, and problem two is to understand my NATO English. You will see. First, what I try to explain in the next minutes, our approach to bring the ground effect technology to commercial use. You see here already with this picture, our example was a swan. A swan has a trailing edge which is parallel to the ground. It has winglets, it has a very big body, and it has a short span, a short aspect ratio, and it has a takeoff aid. Before it can start, he needs the feet to jump out of the water. One of the biggest difficulties to bring our technology in service. The title of my paper is the Hoverwing technology, the bridge between an air cushion vehicle and a ground effect craft. Here, this was the beginning of our Airfish, and this is our Hoverwing, and I will end up with this model. In the moment when we come close to the coastline of the sea or of a lake, our average speeds from land transport drops down to 20 to 30%. On trains, trains and on cars, we have already a speed of 100 to 150 kilometers, and when we have a lake in front of us, it drops down to perhaps 20, 30 knots. So the engineers are trying all the time to reduce the drag during water drive. We started to the beginning with these displacement boats, and then the engineers tried to reduce the wetted area. And the wetted area produced the drag. So many devices were used, and we see on the end the facets of this triangle are boats which are using air for transportation. So the surface effect craft are nearly the fastest vehicles which we have in the moment. So air is a good chance to bring vehicles out of this water, which is 800 times thicker than air. So the only way which we see is to jump out completely out of the water, and so we made two approaches. This is one time the Lippisch airfoil boat and our Hoverwing, which is the same system in principle. Many attempts were made to find solutions to jump out of the water completely. We have on one side the sidewall ships. We have on the other side the seaplanes. And in between we have the tandem wings from Mr. York. We have the real Lippisch design, which we have made together with Dr. Lippisch. Dr. Lippisch was our consultant in my company. We worked very close with him together. And all what I learned from Lippisch. He was my instructor, and I try to go ahead with his idea. And then the last solution is, we call it the second generation, is the Hoverwing technology. Some words from the activities which we have made. We started at the beginning with aircraft. It was an order from our military, from our Ministry of Defense, to look for a craft which can go under the radar and can jump up to increase the radar detection range. So the question was how to solve this problem, and we started with the X113, which is a small single-seater. You see it here flying in the river Weser, and here flying on the North Sea. You see over sand and here over water. This craft had a weight of 390 kilograms. Was a single-seater. Then we started with a six-seater. The requirement was to operate in the Baltic Sea. The Baltic Sea has 80% of the year waves lower than 1.5 meters. So the dimension from this craft came from the sea state in the Baltic Sea. This was this craft. To give you an impression, this craft had already a retractable landing gear. The question from this morning, so we were able also to take off and land on runways, but it cost a lot of weight. And later on, to reduce the loads during takeoff. Then during takeoff with 90 kilometer speed, we catch high loads from the water, impact loads. We installed hydrofoils instead of the undercarriage. You see it here. They were retractable, and they were perfect during takeoff and landing, with some advantages and also some disadvantages. The hydrofoil advantage was that we reduced the loads. During takeoff, we collected sometimes 3 to 4 Gs, accelerations. But with the hydrofoil, it was smooth like a hot knife in butter. The landing was smooth, the takeoff was smooth. So it was an advantage. We made these hydrofoils 60 centimeter long so that the structure was above the waves. This was fine, but then is also the gap between the water and the trailing edge too high, and it increased the takeoff speed. So when you check the pros and cons, they are depending very much where you operate. The next was, these were all military craft, and they asked to have free flight capabilities. We have flown with the X113 at 800 meters high. These craft are very bad aircraft with an aspect ratio of 7. So it's flying in high altitude was not very economic and was also very critical. Then you are always above the stall speed. There was a small gap. But we have fulfilled the requirement, but an aircraft costs a lot of money. I have developed around 14 different aircraft in my life, so I know what it costs. So I tried to find a solution. This is not an aircraft. So we started with a little Airfish. This was a single-seater. You see it here. It was driven by a 30 horsepower engine. In cruise flight, we use 15 horsepower to go 100 kilometer speed. So it was fun to fly. And after that, we went to a higher wing loading, which was not so good. Then the takeoff speed increased. Then we tried the power augmentation system, which are using our friends from Russia, very successful. We learned a lot from you with power augmentation. It helps. And then on the end, we came to the Airfish 3, which is flying now in Australia. We have demonstrated it in Miami during the boat show. It was a big problem when I came to the Coast Guard and said, during this boat show, we will drive with 130 kilometer speed in the harbor. They said that is impossible, and we said, let us try. Typical Americans, they said, okay, show that it works. We have shown, and so we have flown every hour on the hour, so it was very successful. It had a motorcycle engine with 65 horsepower. Cruise speed was 135 kilometer, two-seater. Then we came to the Flight Ship 8. This is this craft. We built it under a specification from a group, investor group in Singapore. You hear we have just finished this work here in February this year. It has a takeoff weight of 4 tons, 8 people. The requirement asks for 180 kilometer speed, 300 miles range, and operation over 2-meter waves. This is this little craft. It is already in Australia. I will record more in my second paper on Thursday when I explain testing of these ground effect crafts. This is a Flight Ship 8, which is now already in Australia for licensed production. In addition, we started with the Hoverwing technology. I will explain it later on, just to say how we came to the theoretical side. We made a lot of wind tunnel tests. We make tow tank tests. We have flown models in free flight and also in a circular circuit. We have worked together with the DFVR in Göttingen, very well known, in Aachen, with the Institute of Luft- und Raumfahrt, and also with the test center for hydrodynamics in Duisburg, Versuchsanstalt für Binnenschiffbau. They were responsible to optimize the hydrodynamics. Altogether, to summarize, you see it here. We started with military craft in the 70s, went to the Airfish technology here, with all these vehicles, which has all flown without any accident, which works perfect. And now we are trying to go up step by step, in small steps, to bigger craft. The results from this testing are, first of all, we have an automatic head stability. This means that you can fly these crafts hands up. We don't like to say flying, we say better flaring. That is the middle between fahren and fliegen in German. So flaring is the right word. So you can really fly it 1 hour without touching the controls. It is automatic stable. You don't need a pilot license. You know the pilot experience. We have a jump capability. On Thursday I will explain what it means, jumping, and what it helps. We have a very high maneuverability. We have turn radiuses of 300 meters. We have very short landings, 3 both lengths. We can flying over ice or sump. We have very compact dimensions. The aspect ratio is in the area of 2.3. We are registered as a boat in the meantime. This was not easy, but now we have it. We have lower inspection costs. We are capside proof, and one important point is that we have no seasickness. A big problem for many passengers is seasickness, and you feel absolutely zero when you are in the air. On takeoff and landing, it is very different. But we have also to accept that we have certain limits. This is sea state. This question came up this morning too, and just to say, our design point is always to fly a tenth of the span. So if you have a craft of 20 meter span, we optimize the craft that we fly in 2 meters height. Then we have the lift to drag in the area of 20. All this is very well known since Wieselberger has detected the increase of lift to drag when depending from the ratio height divided by span or by chord. And this is a prediction of Wieselberger. And what you see is you can double your lift to drag when you come close to the ground. And this is our design point, which is always a tenth of the span. These markings, these points which you see here, are measured points with the X113. So the confidence level to the Wieselberger curve is very high. You see, these are real data flown in test flights. These are the good news. There are some other points, especially stability, but I think it's not necessary to explain it. Already Mr. Obstal has already explained, and our friend from Russia, Professor Rostosvensky, will explain it deeper. So I run over this point and I come to the problem. Here I plotted the measured data on takeoff of the X113. You see, to the beginning we are a displacement boat. Here we come on the step. Here we are a skimmer. And then our ram air try to reduce the weight. And here we are in the air. And you see from this point that we need roughly 2.5 times more power to overcome the peak, the hump-drag, at that speed. And this is the biggest problem to bring ground effect craft for commercial use. You install 2 times more power, but for only 1 minute. You carry the weight. You have to invest the money for the engines, and so this is the biggest hurdle which we have to overcome. Here it is again. So you have to install this amount of thrust to overcome here the peak, instead of having 50% of the power which you need to 90% of your cruising flight. Many attempts were made to reduce this hump drag. We started it already with a high pressure air cushion like a hovercraft. It works, but not very good. The problem is that you have a lot of drag when you have higher waves. Then we started with the power augmentation. Mr. Rostelwetsky will explain it deeper, to have a feeling what it helps and what are the pros and cons. Then we started with the X114 with our hydrofoils, and we ended up with our Hoverwing technology, which is now our best result. To the beginning of my presentation, I showed you that the fastest vehicle in the water are surface effect crafts which use an air cushion. Here I plotted some of the existing surface effect crafts, thrust or drag, versus speed. And you see that the fastest craft is this SAS 100A, which comes already close to a speed which we need for takeoff with ground effect craft. So it was clear, let's use this technology to overcome the hump-drag. Here I compared the Hoverwing result of the Hoverwing 30 in this diagram. So all the crafts which have still water contacts go in this direction, and the only way is to brake here at that point. At that point you must be in the air. This determines the wing loading. And now I'd like to explain to you the Hoverwing technology with the PowerPoint, if it works. It gives you some explanations. Oh, it works already. The question is if I can work it. Herewith I try to explain what is our Hoverwing technology. You see, this is a catamaran boat which has a skirt in front, it has a pylon, it has a center wing fuselage, and this shows on one side the finger type skirts on the front, copied from surface effect ships. We have a back type textile skirt on the rear. We have in the pylon a small gap. We can close it with a door, and there we catch only 7% of the airflow of the propeller. You know, that's not much. Already for cooling an engine down, you need roughly 5%. So with 7% of the airflow, we go through this air tunnel between the two catamarans. One advantage is that our chord length is very high. This is a Hoverwing 80. I will explain where we come from. And you see there the tunnel, and this is fully submerged without an air cushion. When we open the flap on the rear side, then the airflow go between the two catamarans. The pressure fills the back on the rear side, and the airflow build up the air cushion. It starts. The craft starts already to come more out of the water. And in the moment when we have rear pressure between the catamarans and the rear bag, then our figure skirts receive the pressure from the rear side, this flexible skirt, and we are coming more and more with the static pressure, and on the end you will see with the static pressure we bring the wetted area lower. Then between the two skirts we have air pressure, and we are sitting already on air. This means that 80% of the total weight is already carried at static conditions. This means our wetted area is reduced to 20% of the weight. And with that chance we can, we are then able to lift the craft with a minimum of power out of the water. And you see here, this is the situation just before takeoff. And then in the moment when we are completely out of the water, our catamarans doesn't seal the air cushion, so we have no more pressure between the catamarans, and the ram air push the skirt rearward automatically. So we go in transition from an air cushion vehicle directly in a wing and ground craft. Okay. And I think now we can stop this PowerPoint. I hope he stops. Perhaps you can help me that we switch back to this point again. So the advantage of this system is that we are the bridge between an air cushion vehicle and the ground effect craft, and it works also in opposite on landing. In the moment when we it's warm up. In the moment when we touch the water, then it seals automatically with the two catamarans. The air cushion builds up and we have a very soft landing. You will see it then on the video later on when I show the craft in operation. Another point which I have to mention is that we have here, you see this on this picture, that we have the center of lift of the static air cushion between the two catamarans. And to make sure that during takeoff we have not a change in center of lift, then the center of gravity remains on the same point, you have to make a forward swept wing that the center of aerodynamic lift and aerostatic lift is identical. This means you don't need any other control, you just push your throttle forward, and in the moment when you are in the air, nothing changed. This is the same on landing. That is the reason that we make this swept forward wing. Another advantage from this design is that we have here a very big useful room. When you compare to an aircraft, you have roughly 16% of the volume of the aircraft which you build as useful room. We have 40%. This is all room which you can use, and our wing cord is so long that you can sit and stay already in the cabin. This is one of the points, and this cabin is already a wing section. It carries 40% of the total weight by the cabin. In an aircraft, and I'm an aircraft designer, I know what it costs. A cabin costs weight, drag, and a lot of structure. We are sitting already in an airfoil section which produce lift. So the system is perhaps explained with this diagram. I plotted here the vehicles which are independent from forward speed. So on nautic technology we have the displacement boat, and these are crafts which are depending from forward speed. This is on one side the hydrofoil, and in the aeronautic technology we have the helicopter which is independent from forward speed, and the aircraft. And when we go in our ground effect area, we have here the air cushion vehicle, here the wing and ground effect, and we are with our Hoverwing technology just in the middle. It is interesting when you compare the lift to drag between an helicopter and an aircraft. This is roughly 5, and this is roughly 14. It is the same as with an air cushion vehicle and a wing and ground. This means so long you produce your lift with forward speed, you are much better than to produce your lift to compensate the weight only by engines. This is the same ratio between these two craft and this craft. The problem on water-based craft is shown here. Little water planes need a ratio of roughly 3.2 weight to thrust, and conventional wingcraft are in the area of 4. We gained with the Airfish 3 already 5.2, but with low wing loading. With the Hoverwing we are already above 6, and we think with more research work we will go higher in this direction. To study all our Hoverwing technology, we asked our Ministry of Research and Development for some sponsoring, and they said, okay, we will only sponsor if we see that these craft has a commercial chance. So they have written a requirement. This was an independent company, has written the requirement for a craft operating in the Baltic Sea with these data, 80 passengers, 180 kilometer cruise speed, a range of 800 kilometers sufficient for the Baltic Sea, wave height 1.5 meter, 80% of the year, and also takeoff and landing. But they ask also to be able to land in 2.5 meter waves in case of a sudden storm or without a danger to the passengers, and an emergency stop distance of 400 meters, a turn radius lower than 1,000 meters. This was the question this morning, maneuverability. I will show you some test results on Thursday. And then a fuel consumption lower than 40 grams per passenger and kilometer. Installed power lower than 150 kilowatts per ton. And a span lower than 20 meters. Longer than 20 meters is a problem to maneuver in the harbors or in channels and in small lakes. So they said the limit is 20 meter span. To stay in my time. So this was then our design, the Hoverwing 80. And you see here we are able to tilt our wings upwards like on airplanes, on carriers, to remain in the 20 meter limit. This craft, you see it here also, then with the catamaran we are capsule proof, so it is no problem to move our wings upwards. Our big centrifugage offers a lot of useful room. This is on the Hoverwing 88.5 meters. This is the dimension of the Airbus. And when you go to the structure on an aircraft, you have to carry your weight, which is in the middle by the wings, and you carry your bending loads via very heavy main spars. And here we have the lift where the weight is. So we can reduce the structure and offer a lot of comfort. To show you the dimensions, you see we have here already headroom 2.2 meters. This is an airfoil section with 12%, so it costs not more drag, it just have produced 40% of the lift. Lengthwise, you see here 2.7 meter in the middle with 12% airfoil section. To give you a short feeling how it looks like. This is the feeling how it looks inside with the right dimensions. The first class, the requirement are 16% of the total passenger seats have to be first class. It is easy, like the new ferry boats, to have an entrance from directly roll on and roll off with the two ports. This is already with this Hoverwing 30. 30 means 30 persons. So it is easy to get in. So it offers a lot of chances. And when you can go bigger, then you have also the chance to load it from the rear side. The wings are tilted up. Then our Ministry of Research and Development asks also, make it sense to go bigger, or is it limited to certain dimensions? And what we learned, and I think Mr. Rotzemer will say the same, the bigger the craft is, the better it is. 10%, fly 10% of the span. So when you have 80 meter span, you have already a lift to drag of more than 20 when you fly in 8 meters height. And 8 meters waves are not so often. But you can only go on higher sea state when you have the same relative dimension to that. You cannot go with a small boat on the ocean, and this is here the same. This is the Hoverwing 80, the design which we try to build on the end. I think it is necessary to make some remarks to the economy, similar to the diagram which Mr. van Opstal has shown, but here we try to have a better feeling how much power you need. the required power in kilowatt per ton divided by a kilowatt per ton with the standard car. This is a Volkswagen. To have a feeling how much power you have to install it to compare with other vehicles versus speed. Here we have the same results as we have seen this morning. I plotted here the Hoverwing 30, I plotted here the short, and I plotted here the Dornier 27. So you see, when you go with 200 kilometers with a helicopter, you need 8 times more power in comparison to a ground effect craft. 8 times more power is cost, fuel consumption, range, and so on. A comparison with the useful volume, I tried it to make here. This is the Airbus. This is 747, and you see here the useful volume. And this is made with a ground effect craft with shorter aspect ratio, but designed to the same range. And it's interesting, let's say the cabin area of the Airbus is 212 square meter. On the Boeing 747 is 328. An airfoil boat is 900. So we can offer ship comfort and not sitting in high density as in our aircraft of today. Mr. Van Opstal has shown this Gabrieli diagram. It's the same. This is a very well-known Concorde. It's the peak at the moment. So this is a blanket area which gives us the chance to fill. We have done then some comparisons. What is the advantage when we have such a boat in the Baltic Sea? We compare the distance between Kiel and Göteborg as an example. And what is the time to come from Kiel to Göteborg as an example? We checked roughly 50 different routes. And you see, we have the ground effect craft faster than in 80% of our journeys over the Baltic Sea. When the distance is lower than 1,000 kilometers, then we are faster than an aircraft. We can use 700 harbors around the Baltic Sea. We go from point to point. But on an aircraft, you have to go first to Hamburg. You need the first hour by car, and then you check in, and then you have the same point on the other side. So we compare in this case 14 hours journey time versus 4 hours versus 2.5 hours. And so long the distance is slower than 1,000 kilometers. In 80% of our journeys, and we checked all the days, there were 60 million people traveling over the Baltic Sea. In 80% of cases, the ground effect craft was faster when you use the infrastructure from the existing harbors. It is possible to make also some comparisons, but it is too long otherwise to compare the prices. You see, an airfoil boat, ground effect craft, Carno power, whatever it is, has not a pressurized cabin, it has not an undercarriage, it doesn't need all the redundancies. Then we are all the time over the runway. We are able to land at every second, so we don't need the redundancy, and this means that you are minimum 30% less in production cost in comparison to an aircraft same size. And when you look to the money which you need, let me say the Caravan on floats. The Caravan on floats has only 670 kilogram payload. So you have to pay per seat 211,000 US dollars. And with other craft this is identical. And instead of 74,000 D-marks per seat. And when you go for kilogram payload, it is more important. All this was fine. Theory is good. We say in Germany, theory is everybody knows how it works, but in reality it doesn't work. In opposite to praxis, praxis works and nobody knows why. So our ministry said, okay, show that it works. So they gave us the order to build a scaled down model of the 80-seater, that all the technology is identical but just scaled down to the ratio of 3.3. This is the reason that this man is laying in the cabin, and we couldn't find the man also scaled down to the ratio of 3.3. You see here the bag, you see the finger skirt, and here we had a small motorcycle engine, and we have built this craft. Here you see it flying. I will explain the test results then on Thursday. We have installed more than 200 kilogram recording systems to measure everything, power, speed, stability, turn radius, stop distance. I will explain it later on my lecture tomorrow. This is the craft here in flight. You see already the skirt is automatically backwards since the ram air push the thing backwards. Our next step, which we will go, is Hoverwing 20. I feel the step from the little 2-seater directly to 80-seater is too big. There are also some other structure problems in between. So our next project is Hoverwing 20. It is still the same catamaran system, the same skirt. It is in principle scaled up from our Hoverwing test bed to 20 seats to give you a feeling about the dimensions. It will have an empty weight of 6 tons. We have to carry 2,000 kilograms of payload. This is 20 passengers with each 20 kilograms of baggage. This gives a useful load of 2,460 kilograms, so the total weight is 9 tons. We have these dimensions. We are just remaining in the 20-meter limit, which they ask for. We have a cabin height, which is already a cabin length of 6.2 meters with such a small boat, in the width of 5 meters. 5 meters is like that, in such a 20-feet boat, and these are the performance. Our predictions are fairly good all the time when we have built craft, and we have built in the meantime 6 ground effect craft. We have received specifications which we have to fulfill, and every specification we were able to fulfill 100% without any difference. You will see it also in comparisons on Thursday. The craft will have 500 kilometer range, 3 hours endurance, 170 kilometer speed, and a takeoff speed of 126 kilometers. It is very important to keep the takeoff speed low as possible. Then you cannot, unfortunately, receive the CL of 1.8 or 2. Then you cannot rotate in opposite to an seaplane. So the CL which we reach is in the area of 1.1. I think you will have similar results. More is also with flaps not possible, and you have also then the downwash, which is limited with the surface. So we try to have our wing loading that we remain in a speed range, takeoff speed, which is lower than 130 kilometers. We will have a lift to drag of 18, which is already much better than all aircraft which exist now. And we install 460 kilograms for takeoff. On Thursday, I will show you then some test results. Installed power versus cruise power, and otherwise we had to install more than 700 horsepower when we cannot use our static air cushion. So altogether, this is cabin interior from the 20-seater to give you a feeling. And now I'm just in my time. Here I plotted again to have a feeling what is the advantage, what it costs. Unfortunately, the data are data from 90. How much we have to pay to carry 1 kilogram from Hamburg to New York. We can do it with a ship. Then we pay 25 cents per kilogram, but we have a speed of around 20 to 30 knots. Or the other alternative is to go with 400 knots, but then you pay 5 times per kilogram. And we see a big gap between the two transport systems, and our target is to run at that point with these costs, with that speed. And I think we have many applications where a speed of 200 kilometers is good enough. In the end, we have to say, when you find out which system is the best for commercial use, you use the merit factor. The merit factor means payload multiplied with pay volume, multiplied with speed, and multiplied with range, divided by the purchase price and operational cost. This is a key factor when you compare different systems. So if this factor with Wingships will be higher than with aircraft, then we can fill the gap which I have shown before. And so with the fast, expensive air freight and the low, slow, but inexpensive sea freight is our big chance if we work together, all together, to bring these ground effect technology in service, and that we have, and we are here all to build up believers which give us enough money to come in service with these vehicles. Thank you very much.
Well, now it's time for questions. Okay. I remind you to give your name first.
My name is Bo Svensson, I'm from Sweden. That last slide you showed with the price per kilo comparing ships with aircrafts, where would you put trucks on that one? Somewhere in between, but because in Sweden we have a long coast where there's a road inside of the coast, but you could go with a boat just outside.
You see, the key point is the lift to drag. The lift to drag determines the thrust which you need. You convert roughly with efficiency of 75% horsepower versus thrust. So when you have a craft which has a lift to drag of 20, in comparison to an aircraft which has a lift to drag roughly 14 in high altitude, this is the range of the 747 and the Airbus, then this gives you directly the answer how much power or how much thrust you need and how much fuel you need. And when you have the same efficiency, this is the key factor. And believe me, so long we can go to higher span, then our chances to come to lift to drag to 30. This is just a question of dimensions. And when we have 30, then our efficiency is 2 times higher than an aircraft.
Yeah.
But on distances shorter than 1,000 kilometers in the moment.
Yeah,
we cannot go faster than 200 kilometers. A problem of ground effect craft is, to answer also this question, is to have height stability, we need a certain angle of attack. When an aircraft flies, it goes faster, it reduces the angle of attack all the time. When we use the full power, which we need in the moment for takeoff, for cruise speed, then we come to an angle of attack which is negative. And when we are negative, we lose a big portion of the ground effect, and we need also the automatic height stability. So in future, we will go step by step to higher wing loading to increase the speed. Or with another system, you will see it on my results on Thursday, when we have a trailing edge, which we can go negative, and then we can still run with a positive angle of attack, we can go to higher speed, and have still height stability.
Is there any further questions? Yep.
Mr. Fischer, I've just got a principal one. You told us within the chart characteristics of airfoil boats that there is no need of a pilot license.
Yes.
But I've learned by Mr. Obstahl that your boat is category B.
Yes, right.
is there now a need of pilot license or not? I don't know exactly.
Thank you for the question. No, we are registered as a ship, as a boat. This is for sure. We are working with the Germanische Lloyd. Just a remark to that, the Germanische Lloyd has checked our facilities. We are certified first in the world to build commercial ground effect craft under the control of Germanische Lloyd and the ISO 9001, so it is a boat. For jumping, we are using only our kinetic energy. You have only the chance to pull on your control, on your push rod, on your stick or on your wheel, and you jump up and it returns automatically to ground effect and recover automatically. You don't need, like on an aircraft, I am a test pilot also, so I know a little bit of it. You have not to jump up, to pay attention that you don't stall with the high angle of attack, and you have to recover and ground. This works automatically. And with another system, which I really also first time explained on Thursday, is a direct heat control system where we are able now to forget all these things. We have then only a little joystick, also for jumping, and the rest is automatic.
Is it now between A and B or A plus B, or how do you?
No, it is a clear B version.
It's B, first of all,
Yeah.
but there are some special situations where it can move or...
We can jump
Mhm.
with our kinetic energy, but we cannot remain in constant flight out of ground effect.
Mhm.
We had the same question from our Luftfahrtbundesamt.
Mhm.
They told me when you jump 20 meters, you need a pilot license. And I asked him, okay, a ski jumper flies 100 kilometers, 100 meters long, he need a
Okay.
pilot license? Using the kinetic energy.
Mhm. Thank you very much.
Wait.
Hello?
Regarding air leakages of the air cushion, how much are they, and how could you compensate them in a better manner? And how is a way of controlling the mass flux coming from the propeller? Is it only the propeller speed, or there is any other intake or something?
No, we are using only the slipstream velocity of the propeller. You know, we have in the propeller concentration that's 50% behind the propeller diameter. You have half the diameters, but double the speed, roughly. At that point, we install this little door, this gap. So we catch the air from the slipstream, and a small portion of that in a small door, there we fill the rear bag, and then the other part, this is roughly 10%, and the rest going between the two catamarans and the two skirts. So there is no other device to control the pressure. But there is a small speed range. You see, so long we have water contacts, we seal it with our catamarans, and this the two skirts. But when we have reached roughly 90% of our takeoff speed, then we have the situation that, especially on sea state, that then we have a leakage. Then the sealing of the two catamarans is then minimum. And so there remains a little gap between 90% and 100% where we lose some air. We are able to compensate it also when we make our door bigger. Instead of 7%, let's say 10 or 12%. But we feel that with the acceleration we can overcome this little hump drag at 90% of the takeoff speed. So it runs all automatic.
You said such a vehicle could reach directly the airport.
Pardon?
such a vehicle could reach directly the airport, Hamburger airport. I saw there was a slide showing Hamburger airport.
Also, yeah.
What way would you advise I mean, on the ground, to Autobahn or something?
You mean from Hamburg to yeah, okay, this was just a calculation.
Yeah, but it could be a hypothesis. Are there any special highways for catamarans or something?
Okay, in this case we need a craft which has minimum a span of 30 meters. 30 meters is 3 meter waves. We can go also to 30% of the span. But then we need the full power. Then you remember the Wieselberger curve shows the lift to drag versus ratio span height divided by span. And so we are able with takeoff power to go to 30% of the span. This would mean with 80 meter span, das sind das 32% sind up to 12 meters. 20 meters we are able to fly, but it's not economical. But to answer your question, which route we take, we are fighting with our German authorities, and they are very bad. That is the reason that we make all our testing in Holland, which is much easier than in Germany. You know this old joke, in Germany is all forbidden, which is not allowed. In opposite to the United States, there's all allowed, with the exception, which is forbidden. And this is perhaps, excuse me, the opposite in France, where also that is allowed, which is forbidden. And we learned in the previous time in America, it was also that forbidden, which was allowed. So in Germany it's very difficult. So we have now reached a point that our Ministry of Traffic will allow it in the next year to make an operation from Lübeck to Rostock to Stralsund to show them that this is a transport vehicle which is reliable, which is safe, which can operate in mixed traffic also between boats. So we will start with short distances in areas where the waves are not higher than 1.5 meters. So Hamburg is long future.
Okay, my name is Aji Purwanto from NCK Toulouse. I would like to ask you questions on the taking off of the aircraft when the flight changed the phase from air cushion to the airlift. You showed us the finger skirt. When it starts to taking off the thing, there is a stability problem when the skirt start to fold up. You know, there is a pressure difference between front of the skirt and behind the skirt. Is there any stability problem that you find in your tests, and how do you solve that, if is there any? Thank you.
Okay, the cross point is just in this moment when we give up the ceiling with our catamarans against the water. Then in this moment drops down the static pressure completely, and then at this moment is replaced by the ram air. So when you see it in the movie, in the video, you will see that for some seconds the finger skirts move a little bit. So long we have sealed and we have static pressure, the back pressure fills the skirts and they are closed. And then when a gust comes and you suddenly are in the air, then you see that it moves forwards and then it goes back, so it runs normally automatically. And in principle, we have not seen any problem. And the big advantage you will also see in the video, it is on landing, then you have the opposite. The rule said that in the back skirts you must have 10% more pressure than in the cushion to seal it on the back side, on the rear side. Is that clear enough? Thank you. So it's not a problem. It runs automatically. Pressure is pressure, and one compensates the other.
Is there any question? Yep.
Hello, I'm Mats Larsson from Stockholm. A lot of this merit factor the high merit factor, as you called it, is due, I suppose, to that you're using a body lift configuration. I mean, you use the cabin as the wing.
Yes.
Is body lift a much simpler concept for these ground effect crafts than ordinary airplanes? I mean, we don't see any airplanes with body lift configurations, at least yet. Well, just my question is, since it's a very economical configuration from this point of view.
We tried it already in the previous time in all aircraft engineers that the wing is also the cabin. It's a question of dimension. A man is roughly, you need 1.8 meter headroom, and this gives you the minimum height in the cabin. So you need a long chord line that you can reach 1.7 meters. This means with roughly 12 to 13% chord thickness, you need a certain dimension. So long our hoverwing is smaller than 8 persons, then it doesn't make sense. And the chord is too small, and you cannot sit in the cabin. So it is only a chance when the craft is big enough. So our Airfish 8, which we have built for Australia, is a small craft, so we have not selected the hoverwing technology, then they couldn't sit in. And we have selected the Airfish technology, and you have seen in this picture, our pilot is laying like that, and it is only 6 meter chord length with 12% with a Z. So it must be big enough, more than 8, better more than 10 persons. Then the fuselage offer a volume that you can sit in, and it produces also lift. 40% of the total lift is coming from the cabin. You don't need that wing.
But it's because of you're traveling such a low speed range that you can have this thick wing, so to speak, and still have a very efficient wing.
Yes, we are running normally in ground effect craft. I think you are doing more or less the same, between 10 to maximum 13% thickness.
But there are no projects of trying to produce airplanes with a speed range of 400 or 500 kilometers per hour, which has body lift configurations that could be possible to compete with these ground effect aircraft.
Aircraft with high speed have airfoil section with 9%, 8%, and starfighter 4%, something like that. So it is true, but there is a really big difference between an airfoil which is in free flight in comparison to ground effect. This question came this morning. The pressure distribution is different, the downwash is different, the angle of attack is different. On a seaplane you rotate to come to CL max. We can't, and we are in the water. And a flap is not so efficient on a ground effect craft as in a real aircraft. So you cannot really compare the two airfoil sections.
So it's more suitable to have. Oh, okay, please.
I'm sorry, I could maybe add something. So as nervous people, I saw the first drawings 15 years ago of the A380, which was the A3XX, and they were studying a wing, a big wing with a big thickness, and where passenger will be inside. And in terms of pax number, they fit very well between 500 and 800 passengers.
Is there any question? Yes, Bernard?
Bernard Mazur, France. For your demonstrator over wing 20, the last one,
20, yeah.
The cruise height is 1.75 meters. you told on the slide.
Yeah.
1 meter.
I can put it on. This was, you mean this one? The 20?
Maybe.
This is not ground effect speed, sorry.
I think it is the last one, yes. Yes,
You
okay,
mean these
okay.
dimensions, yeah.
So you see at the bottom, cruise
Yes.
height, 1.75 meter. Why is it so high?
The cruise height,
The cruise height, yes, is 1.75 meter.
cruise height,
And the-
1.75 meter, yes.
Yes, and the efficiency is 18. 18. Lift over drag is 18.
Yes, the lift to drag is 18
Yes.
in that height. When we come closer,
Yes.
then it is better.
Yes, but why the cruise height is so high?
This comes
It-
from the Baltic Sea, where
Because of the waves.
are 1.5 meter in 80% of the year.
No, because of the waves.
Of the waves.
Okay.
The
But
Baltic-
if there were no waves, for instance,
then when we have
What could
low
be the
sea
cru-
state, then we fly much closer and we are much better. But the economy asks that we can use 80% of the year
yes,
a
okay.
craft in the Baltic Sea. And
Yes.
when the waves are in 80% of the year 1.5 meter, we have to make a
Okay.
design where we can live with that lift to drag
Yes.
in that height.
But you said after that for Boeing 747,
For seven, yeah.
the lift over drag ratio is about 14.
14 in high altitude.
Yes, at high altitude. So
Otherwise they
you
are lower,
compare
further.
a Boeing 747 and your overwing,
Yes.
the lift over drag are about the same,
Yes,
14 and 18.
when you really compare the two things, a Boeing 47 with this dimension of the Hoverwing, 20, then it is true. But when you
Aye.
compare a Boeing 747 with a ground effect craft, then you have to go to a craft which has 60 meter span. And the
Yes,
60 meter span,
With
in
the
this
same
altitude, you have a lift of more than 30.
30.
30.
Okay, thank you. In the same
Yeah.
sea states.
Wieselberger, 2 times.
Sea state.
Yeah.
Yes.
In the same sea state. And
Okay,
it is
okay.
only a question
Thank you.
dimensions, relative dimensions.
Yes, Mr. Duc.
Jean-Michel Duc from Joseph. I would like to come again on your merit figures. Could you show the I think your last chart where you produce the merit figure with a payload, pay volume, distance, and so on? Because I think we might discuss a little bit about this. Yes, but the one with the formula, the
Merit factor.
the merit factor. You
Yeah.
have one chart with the formula.
This is here. It is.
Oh yes, here it is. I'm sorry. Okay. I have just the feeling that, or may I ask a question, why do you count twice payload and pay volume? I would choose either one or the other, because I think, is it fair to use it twice? Either you have very high density payload, or you have a low density payload, but you maybe could.
Okay, there are 2 answers. I will show when you make a glider, high performance glider, then you have a pilot with 90 kilograms, but you sit like that. So no pay volume. Payload is the same. The other point is when you fly first class in an airliner, you have the same speed, you arrive at the same time, and you pay 50% more, only for the volume. So the question is comfort and payload, in principle. Perhaps you can make factors and say this is 0.8 or something like that, but the principle is how, for what cost you transport volume and weight over a certain distance with a certain speed. That on the end the answer. And every craft has an optimum for certain missions. Yeah. More than 1,000 kilometers, I would prefer the 747.
Yeah.
Sasha Mavrovic, Zagreb. Your government set requirements for range 800 kilometers, but
yes.
Your performance is 500 kilometers. Would that be a problem to getting financing?
No, the requirement from the government was for the 80-seater. And I said the step from the little 2-seater to the 80-seater is for me a little bit too big. I prefer small steps better than one too big. You run into disaster, perhaps. So we said, okay, the little 20-seater don't need these 800 kilometers. There was given, our Ministry of Economics gave a study to a research company in Rostock on the Baltic Sea, which has checked the market. I have data here, but it is too long, where you see how many passengers are going from Copenhagen to Petersburg, what is the price, what is the time, and then to find out how big is the gap. And we found in principle that roughly 30% of all passengers which are moving in the Baltic Sea can be replaced with ground effect craft under these limits in distances. And this gives 320 craft altogether. So we have a big market. If you know, I can show you that. Perhaps I have it fast enough. I'm sorry, I don't find it so fast. So it is here. Yeah, here it is. Here you see the potential of WIG craft, result of the study. In Europe, with different sizes, 60 seats, 120 seats, 180 seats. And on the right side, worldwide. So you can see that we have in the range between 200 up to 250 kilometers, so many faxes, in the range of 250 to 500, so many, and on longer distances it's reduced. This is a question of the speed. And when you now take all the passengers which has flown over the, not only flown, also going by ship, we have this number of craft with different seats to find the best marketplace. And this came out to 80 seats. You see, 2,003,000 has flown with an aircraft on the Baltic Sea per year. So we have worldwide the chance to build 490 wing and ground craft. I think a gap which is big enough.
Another question, or operational question. Maybe it's idiots, my question. We see. When you will be allowed to fly over a river, what is your the way to cross bridge or fly under, over? And is there, we know there is a ground effect. Is there a sailing effect which could disturb the lift?
Mainly we have three modes. When we are in high density or in the river or we go out of a harbor, then we run in displacement mode. We have on our wingtips 2 water propellers, and we have a joystick, and we control with the water propellers go forward, go rearward, or one forward, so we are maneuverable. So during high density in the harbor, we go on displacement. And when we have a certain, let me say, a certain distance which is free, we can see, then we go on step taxi, like seaplanes. This is, we run with 80% of our takeoff speed. There we have still water contact. We have then a very short stop distance, and we have high maneuverability. And only when we have a clear distance in front of us, then we go from 80% speed to 100% and we are in the air. So you have to check it like on a seaplane. Step taxi, or maneuvering, or flying. Jumping is only the last solution. You will see some test results on jumping on Thursday. Then you have a clear answer how far and how high and what's the distance in front of it.
So but do you think you will be one day allowed to fly on the river?
We have with the X113, which was able to fly. There we have flown in the river Weser, and then we make a turn on the land, going out of the river, flow over the land and come back when the river was small. But I will say that is not good for every pilot. This was only to see what's possible. No? Personally, I've flown all our vehicles, and thus is a joke when we flew in the Lake of Constance the first time, and the water police had a lot of questions and obstacles, and we flew with high speed directly to the police boat, and then we jumped over. It cost every time a bottle of whiskey, but it was very impressive. You will see it tomorrow on the video.